This video discusses how to obtain the trig ratios for 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Also, please do not forget the radian values of these popular angles. Remember, 180 degrees is equal to pi radians. Therefore, 0 degrees is equal to just 0 radians. 30 degrees is equal to 180 degrees divided by 6. Therefore, 30 degrees is equal to pi over 6. 45 degrees is equal to 180 degrees divided by 4. Therefore, in radians, it should be pi over 4. 60 degrees is equal to 180 degrees divided by 3. Therefore, in radians, it's pi over 3. 90 degrees is equal to 180 degrees divided by 2. Therefore, in radians, it's pi over 2. Now, we are going to look at how to derive the trig ratios, sine theta, cosine theta, and tangent theta, when theta takes each of these specific angular values. First, we will look at the 0 degree angle. We are going to need a construction. As always with the trig ratios, we are going to need a right triangle. Of course, I cannot draw a right triangle so that one of the three angles is equal to 0 degrees. Therefore, I will draw a simple right triangle with an angle labeled as theta, and then we will argue what happens if this theta is approaching to 0. So here's my right triangle. The angle right here should be equal to 90 degrees, and I'm going to label the angle right here as angle theta. Let me assume that this side, which is the adjacent of theta, is of length A. Let me assume that the height of this triangle, or the opposite side of theta, is of length B. Let me assume that the hypotenuse is of length C. We know by definition sine theta is equal to opposite over hypotenuse, which should be B over C. Cosine theta is equal to adjacent over hypotenuse, which should be equal to A over C. Tangent theta, which is defined as opposite over adjacent, should be equal to B over A. However, for this case, I'm interested in 0 degree angle. That means I need to see what happens to these sides A, B, and C as theta approaches to 0. So if theta is approaching to 0, what will happen to these lengths? If theta is approaching to 0, can you see that the height B should also be approximately equal to 0? Therefore, as theta approaches to 0, B should approach to 0. When B is approximately equal to 0, what can you say about the lengths of A and C? Those two sides should overlap. Therefore, the length A should be approximately equal to the length C. According to that argument, now we can quite easily give values for sine theta, cosine theta, and tangent theta when theta is equal to 0. Sine 0 degrees, since it's equal to B over C, and because B is approximately equal to 0, this ratio now becomes 0 divided by C. 0 divided by C is equal to 0. Cosine 0, which was originally defined as A over C, and when theta approaches to 0, we know A approaches to C. If A and C are equal to one another, A over C ratio should be equal to 1. Tangent 0. Tangent theta was defined as B over A. As theta approaches to 0, we know that B approaches to 0. Therefore, tangent 0 degrees should be equal to 0 divided by A, which is equal to 0. So we just derived sine 0 degrees, cosine 0 degrees, and tangent 0 degrees. Try to remember that sine 0 degrees is equal to 0, cosine 0 degrees is equal to 1, tangent 0 degrees is equal to 0. Now we will see how to derive the trig ratios for 30 degrees and 60 degrees. The trig ratios can be derived for both of those angles using the same diagram. We are going to need an equilateral triangle whose each side is equal to 2 units. Let me go ahead and draw an equilateral triangle. Now, can you tell me the size of the angle right here? Since this is an equilateral triangle, each angle should be equal to 60 degrees. So let me label it as that. This angle is equal to 60 degrees. Let me also show the length of one side of this equilateral triangle. That side has a length of 2 units. Now what I'm going to do is I'm going to draw a perpendicular bisector from this vertex to this base. Since it's perpendicular, this angle right here should be 90 degrees. It's a perpendicular bisector, which means what should be the length of this part of that base? Since each side of this equilateral triangle is 2 units long, the highlighted part of that side should be equal to 1 unit. Now, can you tell me the size of the angle right here? That angle should be equal to 1/2 of the complete angle right here. Since the complete angle is 60 degrees, 1/2 of that should be equal to 30 degrees. Therefore, the angle right here is equal to 30 degrees. Now, if I know the length of the green bisector, then I can write down all the trig ratios for both of these angles, 30 degrees and 60 degrees respectively. Can you tell me the length of the green perpendicular bisector? As you can quite easily see, we can focus on this left half of the equilateral triangle. That left half is a right triangle. According to the Pythagorean theorem, the green bisector must have a length of square root 2 squared minus 1 squared, which is equal to square root 3. Now we can quite easily write down all the trig ratios for 30 degrees and also for 60 degrees. First, we will go ahead and write down the trig ratios for the angle 30 degrees right here. Note that for that 30 degree angle, opposite is of length 1 and adjacent is of length square root 3. Hypotenuse is of length 2. Therefore, sine 30 degrees, which is defined as opposite over hypotenuse, should be equal to 1 divided by 2, 1/2. Cosine 30 degrees, which is defined as adjacent over hypotenuse, should be equal to square root 3 divided by 2. Tangent 30 degrees, which is defined as opposite over adjacent, should be equal to 1 over square root 3. Similarly, we can write down the trig ratios for the 60 degree angle right here. Note that for that 60 degree angle, opposite is this side, adjacent is 1, and the hypotenuse is 2. Therefore, sine 60 degrees should be equal to opposite over hypotenuse, which is square root 3 divided by 2. Cosine 60 degrees should be equal to adjacent over hypotenuse, which is 1/2. Tangent 60 degrees should be equal to opposite over adjacent, which is square root 3 over 1, which simplifies to become just square root 3. Now we will look at the trig ratios for 45 degrees. In order to obtain the trig ratios for 45 degrees, I'm going to need an isosceles triangle. Not just an isosceles triangle, I need an isosceles right triangle. So here's the isosceles right triangle. I need each of the two equal sides of the isosceles right triangle to be equal to 1 unit in length. Note that the angle right here is still 90 degrees. If each of these two sides is equal to 1 unit, what should be the length of the hypotenuse? According to the Pythagorean identity, once again, it should be the square root of 1 squared plus 1 squared, which is equal to square root 2. One more question. What should be the size of this angle? Since these two sides are equal in length, this angle should be equal to this angle in size. Therefore, each of those angles should be equal to 45 degrees. Now, with respect to the angle shown right here, this is the opposite, this is the adjacent, and right here is the hypotenuse. Therefore, we can quite easily write down all the three trig ratios for 45 degrees. What should be sine 45 degrees? Sine 45 degrees should be equal to opposite over hypotenuse. Therefore, it should be equal to 1 over square root 2. Similarly, cosine 45 degrees should be equal to adjacent over hypotenuse, which is also 1 over square root 2. Similarly, tangent 45 degrees should be equal to opposite over adjacent, 1 over 1, which simplifies to be equal to 1. Finally, we will look at the trig ratios for 90 degrees. Of course, I cannot draw a right triangle with another angle being equal to 90 degrees. Therefore, just like for the 0 degree case, I'm going to draw a usual right triangle and then argue what will happen to the geometry as the theta increases to 90 degrees. So here is a usual right triangle. This is equal to 90 degrees. I'm going to label this angle as angle theta. Let me assume that the length of this side is equal to A. Similarly, let me assume the length of this side to be equal to B. Let me assume that the length of the hypotenuse is equal to C. Now we need to argue what will happen to these lengths if theta approaches to 90 degrees. If theta approaches to 90 degrees, what can you say about the point of intersection of this side and this side? The point of intersection is right here. However, as theta increases, the point of intersection right here will go further and further away. That means technically B and C will be really large. Think about a case like theta being equal to 89.99 degrees. In that case, these two lines of lengths C and B respectively will intersect. However, that point of intersection will be far away. And in that case, the sizes of B and C will be approximately equal to one another, and also the length of A can be negligible compared to the lengths of B and C. So let's go ahead and write down that summary. As theta approaches to 90 degrees, B will be approximately equal to C, and B and C will be very large compared to A. That means A divided by B will be almost equal to 0. A divided by C will also be equal to almost 0. So remember that B and C are very large. Now we can write down the trig ratios. If the theta right here is approaching 90 degrees, I will directly write down sine 90 degrees. We know sine 90 degrees should be opposite over hypotenuse. As theta approaches to 90 degrees, we know that B and C are approximately equal to one another. Therefore, B over C should be equal to 1. Similarly, cosine 90 degrees. Cosine 90 degrees is equal to adjacent over hypotenuse, A over C. Since A is very small compared to BOC, A over C should approach to 0. Therefore, cosine 90 degrees is equal to 0. Tangent 90 degrees. This should be equal to opposite over adjacent. Since the opposite is very, very large, the opposite over adjacent should also be very, very large. That means tangent 90 degrees should approach infinity. However, there's a small catch. When theta is such as 89.99999 degrees, tangent of that angle is actually positive infinity. On the other hand, if that theta is a little bit more than 90 degrees, say for example, theta is equal to 90.000001 degrees, in that case, tangent of that theta approaches to negative infinity. You will learn that in details in a future section. Because of that reason, we can simply argue that tangent 90 degrees is undefined. However, there's an easier way to come to that conclusion. We know tangent theta is also equal to sine theta divided by cosine theta. Therefore, tangent 90 degrees should also be equal to sine 90 degrees divided by cosine 90 degrees. However, cosine 90 degrees is equal to 0. 1 divided by 0 is undefined. Therefore, we simply write down that tangent 90 degrees is undefined. Now we have derived the basic trig ratios sine, cosine and tangent for all the popular angles: 0 degrees, 30 degrees, 45 degrees, 60 degrees and 90 degrees. They are all going to be extremely important. So let's go ahead and write down a summary of all the results that we derived today. Let me draw a table to write down the summary. Theta on the first row, we are looking at 0 degrees, 30 degrees, 45 degrees, 60 degrees and 90 degrees. It's also very important to remember those angle values in radians. We know that 0 degrees is equal to 0 radians. 30 degrees is equal to pi over 6 radians. 45 degrees is equal to pi over 4 radians. 60 degrees is equal to pi over 3 radians. 90 degrees is equal to pi over 2 radians. Now we will fill this table. I'm going to need sine theta on the first row, and then we will write cosine theta on the second row, and then we will write tangent theta on the third row. What was sine 0 degrees? Sine 0 degrees was equal to 0. Sine 30 degrees was equal to 1/2. Sine 45 degrees was equal to 1 over square root 2. Sine 60 degrees was equal to square root 3 over 2. Sine 90 degrees is equal to 1. Now let's go ahead and write down cosine theta. Cosine 0 degrees is equal to 1. Cosine 30 degrees is equal to square root 3 over 2. Cosine 45 degrees is equal to 1 over square root 2. Cosine 60 degrees is equal to 1/2. Cosine 90 degrees is equal to 0. Remembering this table is extremely important, especially for future work. Now I will also tell you a short trick to remember this table. If you can remember just one line of this table, let's say you remember sine theta values for these specific angles, then the other two rows can be easily deduced. Cosine theta is the same sine theta backwards. You can see that sine theta from left to right is equal to cosine theta from right to left. We will also see tangent theta. We know that tangent 0 is equal to 0, tangent 30 degrees is equal to 1 over square root 3, tangent 45 degrees is equal to 1, tangent 60 degrees is equal to square root 3, and tangent 90 degrees is undefined. It's also easy to deduce tangent theta if you simply fill out the first two rows. Tangent theta is simply the ratio between sine theta and cosine theta. 0 divided by 1 is equal to 0. 1/2 over square root 3 over 2 is equal to 1 over square root 3. 1 over square root 2 divided by 1 over square root 2 is equal to 1, and so on. Finally, tangent 90 degrees is 1 over 0, which is undefined. Please try to remember this table. You can thank me later. All right, that's it for the discussion today. Thank you so much.